Hey, what's up, guys? This is Chung here. So today, let's take a look at today's daily challenge, number 425, word squares. I think it's a cool problem here. So you're given like a set of words without duplicates. Find all word squares you can build from them. Okay, and the sequence of words formed a valid word square if the case row and column read exact the same thing. So this is one of the examples here. Basically, with the words ball, area, lead, and ladies, it forms like a square. Basically, every uh, on each of the row and columns, the uh, the letters, the strings are the same. For example, the ball horizontal with the BAL, and also vertically it's also a ball. And the second one is area, so the area is like same thing. This is also area, right? And the lead, this is also a lead. And then the last one is a lady. Okay, so which means this is a valid answer here. As you guys can see, the sequence matters here, right? Okay, and it asks you to return all the possible word squares given like a list of the word here. As you guys can see, the size of the size of the word square is the same of the length of the word here. So the the main the main intuition for this problem is that basically given like a list of words here, we're trying to basically we're trying all the possible all the combinations. So first we're adding a ball here. Let's say we're adding like a ball BALL. Basically we're trying to try the ball first, and then we try the area, and then we lead, and we try ladies. Let's say if we try ball here, okay. If we put the balls on the first one, so what's going to be the second one? So the second one, with anything, so this is going to be the second word here, right? So what's going to be the second valid, the second valid answer for this, right? The second valid. So for to be able to satisfy this word, so the word has to be starting from what? Has to be starting from A. Because as you guys can see here, if the word starting from A here, basically if the prefix is the same as if the prefix of this word is the same as the prefix vertically, then we know, okay, so this one is a candidate. We can use that. In this case, is an area here. So that's why, since the area here has the prefix of A, which is the same of this one. That's why uh, the second one is area here, A, R, E, and A. Okay. Now, so now it's time to fill in the third word. So same thing with the when we are filling the second one. So to fill the third one, as you guys can see, it has to be what? The prefix has to be equal to the LE here. Okay, because we need the word to be the same as horizontally and vertically, right? That's why, I mean, the prefix of the second word of the third word has to be LE, which in this case has to happen to be the what LEAD, right? And then the last one, of course, the prefix has to be a what? LAD, LAD, and we're looking for the LAD and Y. Cool. And we're doing this for all the words. So now I think for this part, I think it's pretty obvious that we're gonna use like a backtracking problem, right? And at each of the step of the backtracking functions here, we need to, so as you guys add, besides the backtracking here, so and by the time we reach the last one, the last row here, then we know, okay, we find a valid square. Otherwise, we just abandon it. Now the problem comes down to how can we find the prefix of a word by given this like a word list here. I mean, we can of course use the hash table. Basically, I think the hash table, the key will be all the prefix, and the value gonna be the list of that word, the words who starts with the same prefix, right? That's the hash table solutions. And another solution is by using the a trie, right? I try TRIE, right? TRIE, the trie structure is famous of basically it's also called a prefix tree. And this is also like a good candidate of solving this kind of problem. Basically, that's exactly what we need. We need a prefix. Uh, we need to find all the words with the same prefix. This thing I think if you guys have seen like system design problem, there's like Google like a search recommendations, right? Basically, if there's a search bar here, if in Google there's a search bar, basically you type in the ABC here, and here and down here it will give you like the first some recommendations, right? Start recommendation sentences or words starting with ABC, okay, right? Basically it will give you I think the top 10 most popular one. That's okay. So the way the Google implemented this or that for that interview problem, I think it's we usually just use the trie structure to store that. Basically, as you guys can see, this is exactly what this problem where it's asking us to find. Basically, you are given like a prefix, and we need to utilize the trie structure to find all the words, right? That's starting with this prefix, and then for each of the word, we can basically we can try each one of them, right? Mm, cool. So with that being said, let's try to create this the trie structure here. Uh, okay. You know, to create the trie structure, uh, usually we need a like a node here, a tree node. I'm just going to call it a node here. And in this node here, we will have like two. We usually have two properties. Okay. So the first one is the children. Okay. The children it's a dictionary basically. The key is the character on this node. And the value is all the child nodes for the current node. And the second one is like for the normal template, the second template, second property of a node is the word. Basically, this property tells you if this node is the ending of a word, and that can help us, find the all the words from the prefix. Basically, the way we're finding it is like this. Let's say if we have like a here we have a here, right? And then we have I think the root node is empty. Here we have a B, right? So here we have a C, D. Let's say the prefix is A and AC. So now the last node is this one. Now whatever under C here, right? Let's say we have a word here. This is a word here. This is also a word, and this is also a word. So basically, and then we're gonna have like three uh then basically we'll have three words here. We'll have three words for this thing here. this is the word 1, word 2, and word 3. And our helper functions just basically will just take any prefix, and then it will return a list of the words that having the same prefix. And you know we can do this, right? I mean, we can do the self dot word itself, and then we can store the word on each of the leaf node here. Okay, but then so for that, I know it's gonna be a little bit time consuming, because the way, and then if you're only storing that the word I mean on the leaf node, okay, then to be able to find all the words having the same prefix, after we reach this node here, we're gonna do a DFS search. Basically, uh, we're gonna traverse all the subtrees from this node until we have find all the leaf node that's marked as the is word equals to true. Okay, and then we're gonna read that value and return it. Instead, what we can do here is we can add each of the node here, even it's not the leaf node, we can also like store like a list of words, that's, I mean, uh currently like starting from this character. Basically, for A here, right? If we have like uh let's say the word is A B C, A C D, A C D, and A B B. So here at the node A here, we're gonna store the list of this all three words: A B C, A C D, and A B B. And here at C here, we're only gonna store the ACD here, because that's the word that has the prefix of A and C. Basically, what we're doing here is, instead of marking using the leaf node, we're adding like one more, or like adding one more like properties on each of the node here, and where this properties here is gonna store all the words that having the same prefix up until this node here, and we're going to populate this these properties while we're building this prefix tree, or like a trie, right? And so that later on, right? So that later on, when we trying to get the prefix, all we need to do is we just use the prefix here, and all we need to do, we just traverse to this last node here, and then we'll be using that words properties of this node. Then we can quickly get our the words having the same prefix. Cool. So, all right. So that's that. And let me continue building the tree node here. So we have a tree node here, and for to build the trie structure, we need two helper functions. Now to build it, we only need the one add here. Basically, the add is to add this word into this trie, right? The prefix tree. And to do that, we need like a root. Uh, we need a root first. So here, current equals to the root, okay? And then for character in the word, for those who still don't know how to implement the prefix tree structures, I highly recommend you to try and look for one of the templates, and then try to remember how to populate or how to build this prefix tree. Basically, the way we're building it, we are for each of the word here, right? I mean, we have to maintain like a root, because for the prefix tree, the root is always it's empty. It's empty. That's why I'm creating an empty node as a root node, and anything after that is part of our prefix. So basically, for C in the words if C is not in the current dot children, okay, it means that, okay, if the C is not, if it's not here, we are going to create a new node to hold this C here. Basically, we're gonna have like a node current, right, current dot children C equals to the node. Okay, I mean, every time when we create a node, you know, since the uh, a children, right? A children is a key value pair, and the key is the current character, and the value is another node. See, basically, if there's like a C here, right, and another node is children here. It can have many other children here. That's why each of the child is a node, is another node. That's why I'm creating a node type assigning to this children here. Okay, and then we just need to update. We just children.c. Okay, now we just need to assign this current one with the child node so that we can assign the next character, right? After this the new child nodes here, or if there's if there is already one here, we can simply skip this one here. But we still need to keep moving forward down the road. Basically, if there's a like A here, and then we have a B, C here. Now we're at A here, so we're trying to find B. If there's a B here, then fine, we'll look for C here. And cool, so that's that. And remember, we're trying to also populate these words for each of the node here. So what it means that for each of the node here, right, we're gonna current dot words dot append the current word. This is a little bit of variations of the traditional uh, trie structure here. Basically, for each of the node here, we're appending the word to it. Okay, cool. And yeah, so to populate, to build the trie, right? So we just need to do this. Add word. Now we have a trie structure here, and the next one is gonna be the, let me try do this. Build trie. So the next one is the backtracking. Okay, and backtracking. So we have an answer here, right? The answer is this one. And we try all the possible words, okay? And for word in words, okay? We'll do a backtracking, okay? We'll do a backtracking, and the backtracking basically will have like two parameters. The first one is the index, is the current index, and the second one is the current list of words, because at the beginning, right? So we always assign this word to the current one, to this list here. So then in the end, we simply return the answer. Yeah, that's basically the backtracking structure. And to implement this backtracking method here, let me do this. Basically the backtrack. Okay, we have an index, right? So the index, and then we have a current words. So if the index equal to the n, oh, what is n? The n is this. So the n is the length of the size of the this square, right? Which is the what? The length of the words, right? We can pick any words here because all the words have the same length here. If this thing is n here, and then we know, okay, we have find a valid word square, we can simply append this current words, right? And we do this. Since we're going to do a copy because this current words is gets updated constantly, and we don't want our answer also gets updated. That's why we do a clone here, and then we return. Otherwise, if we haven't reached the end, we need to get a prefix, right? So the prefix. So what's the prefix? We have the index here, right? So the index is what? The index is it's how many is the places, right? So let's say if the index is 2, or let's say if the index is 2 here. So index 2 means we're at here. It means that we'll have like 2. So we're going to get the prefix from this column here, right? And how many strings we have? Basically everything inside our current words here, we're getting the third characters from each of them to form the prefix. Okay, so that's gonna be join. Okay, join what? Join this is a little bit of shortcut of so we have a word of index. Okay, right? For words in current words. Right. So basically what I'm doing here is for each of word in our current words list, I'm getting the this index word from each of the word, and then I concatenate them together to be our prefix. Okay. And then we're gonna have a words here, right? So the word's gonna be we're gonna have like another helper functions, right? So we're like I said, this helper function is going to give us all the words that starts with this prefix. And then for words in words, we're gonna, because only those words are the valid candidates, right? That can keep moving forward, right? So that we're gonna add the current words append to word, right? And then we have a backtracking index +1 because we have already include one more word here, and then current words. Since since the current words is a list, we have to remove it afterwards, so that the next for loop will have the same state, right? Yeah, so that's that. And now, yeah, now the get words helper functions here, right? So the get words is a prefix. Okay, so to get a prefix for get a word with the same prefix, we need to do the same thing. We have to get the root first, and then for C in the prefix. Okay, and basically if C is not in current dot children, as long as any of the prefix is not in the current tree structures, and then we know, okay, so we have nothing. We have 0 word that starts with this prefix. Okay, so that's why we can simply return an empty string here, empty list here. Otherwise, we just keep moving downwards, right? Just like what we did in the add helper functions there, right? So, and that now, so if everything works fine, now we're at the end of the prefix. And so here we can simply return the current dot words. Yeah, because the current dot words stores the all the words that's having this prefix. As you guys can see, if we are not using like these words, adding these properties, basically from here onwards we have to do a DFS search, right, to find all the trying to find all the subnodes starting from this current node here. So this is gonna save us some time here. Cool. So, and yeah, I think once we have all this stuff here and we have a backtracking here and we have this, yeah, I think that's pretty much it is. Let me try to run the code here. Yeah, cool. It's accepted. Submit. Yeah, so it works. I mean, uh, so how about the space and time complexity, right? So, and let's see. The space complexity, the time complexity is uh, we have a word here. So the length of the word is, okay, so let's say this is n here. Let's say we have n words here, okay? So that's why we have an n here. And each words have like, the word length is at least one, at most five, okay? Then we have a n times five. Yeah, because to add this word here, we need to loop through each of the word, okay, which is the mm, for prefix. Okay, we need to loop through the sorry, add here for each of the word. Yeah, we're gonna have like the n times five to add this word into the this prefix tree here. And then for the backtracking, right? That's the n times five. For the backtracking here, we have like we also have n here, n times let's see. So I think the backtracking time complexity is a little bit tricky because here, we have a n here, and for our like prefix tree here, from one of the node, there are like total like what? How many children that can this one node have? Can this one node have? It can have up to 26 because everything's in lower ladder. That's why at each node there are like 26 in total. So the other loop is n, and the inner loop, right? To backtrack all the possible words here, it's n to the 26. It's n times 26 to the power of 5 here. I mean, the word length is at least 1 and at most 5. So it's going to be at 26 to the power of 5. Okay. And that's the number of the backtracking, right? And inside of the backtrackings, we are uh, we are doing this. We're doing like this the number of the so this part is the current words. I think this is 5. This is L, right? This is 5 here because at most we will have like 5 here. And how about this gets words here? So the gets words here, we're looping through from the first one, from the first node all the way down to the to this space to this node here. This will take L time. Yeah, so it's gonna be another 5. Yeah, because the way we're doing like this get words here, we'll spend like the this the amount of the prefix and to get to the current node, and then from here we just get it from there. We just get the words from there. Yeah, so yeah, I think that's the time complexity. And for the space complexity, right? Space complexity, we have like uh we have in total n words, right? So in total we have a n times what? Of each of the nodes here, we have we can store up to 1,000, up to this n length of the words here. Okay, and how many nodes we have here? We have like let's see, we have so basically we'll store like this is L. Let's say this is L. We're gonna store like L times of the words for each of the nodes here, for each of the words. So the space complexity is going to be n times L in this case. Space. Yeah. Cool. Yeah, I think that's it for this problem. I know the time and space complexity analysis is not that clear for this problem, but I think that's not the most important thing for this problem. To me, that the most important thing for this problem is that you have to be able to find a way, right, of of start solving this problem, which is the basically the backtracking, right? We just try to put the words into the square one by one, okay? And we're basically trying all the possible ways. We try the first word, and then we try the second, and we try the third one. And for each of the word here, we try to start from here. We're trying to place the candidates to the next one until we have filled the entire word square. And to do that, we will need to I mean to get the words list based on our prefix, and then we just continue our backtrack uh, logic here. Okay, I think that's pretty much I want to talk about for this problem. I don't know why I feel so tired. Maybe I don't know why, because this is maybe the explaining the tries the prefix structure is kind of annoying, or I'm just having a hard time trying to explaining this problem to you guys today. Sorry about that. But anyway, thank you so much for watching the videos. Stay tuned. See you guys soon. Bye bye.